How exactly does a chemical reaction power the device you're holding right now? Really think about that for a second. There are no moving parts in there, no tiny gears, no visible engine. Yet your smartphone or laptop is running on this continuous, totally invisible flow of energy. We take it for granted because it feels so seamless, but it relies on, honestly, one of the most fascinating intersections of physical science out there. So let's dive into this explainer and demystify the invisible mechanics keeping our modern lives fully charged.
Welcome to the Explainer. Today, we're jumping headfirst into the brilliant world of electrochemistry. This is basically the ultimate bridge between abstract physics and the everyday tech you carry in your pocket. It's the branch of chemistry dealing entirely with the back-and-forth conversion between electrical energy and chemical energy. We're going to see how we can force stubborn chemicals to react using electricity, and on the flip side, how we can trap those chemical reactions to give us portable power on demand.
Here's our quick roadmap for today. We'll start with the rules of energy, then move into how electricity flows, check out forcing chemical change, and finally wrap up with harnessing chemical power.
All right, kicking things off with part 1, the rules of energy. Because before we can command electricity, we kind of need to understand the thermodynamic playground we're working in.
So in thermodynamics, a system is really just whatever part of the physical universe we happen to be studying at the moment. Could be a battery, could be a biological cell. And there are 3 types you need to know. Think of an open system like a hot cup of coffee with no lid. It exchanges both energy, which is heat, and matter, the steam, with the room. A closed system is that same cup, but with a tight lid on it. It still exchanges energy, it'll get cold eventually, but the matter is trapped inside. And finally, an isolated system is like a perfectly sealed thermos. It exchanges neither energy nor matter with the outside universe. Pretty much every electrochemical cell we're going to talk about today operates within these basic rules.
Now, when energy changes, we measure something called enthalpy, represented by the letter H. On the left here, we have exothermic reactions. These release heat out into their surroundings, so the enthalpy change is less than 0. If you were to dissolve sodium hydroxide in water, the container literally gets hot in your hands. But on the right, we have endothermic reactions. These absorb heat from the surroundings, meaning the enthalpy change is greater than 0. Dissolve some potassium nitrate in water, and it pulls the heat right out of the environment. The container actually becomes cold to the touch. Heat pushes out, or heat pulls in.
And to actually measure that heat transfer, we rely on a very specific magic number, 4.18. That is the specific heat capacity of water measured in joules per gram Kelvin. Basically, the specific number tells us the exact, precise amount of heat energy you need to change the temperature of 1 single gram of water by exactly 1 degree Kelvin. It's incredibly useful because it gives us a mathematical way to track all this energy flowing in and out of our systems.
So now that we've got a handle on how energy transfers, let's jump to section 2, how electricity flows. We know energy moves, but how does it physically get from point A to point B?
Okay, we really need to clear up a massive misconception here. There are actually 2 entirely different ways electricity flows. Over on the left, you've got metallic conduction. This is what's happening in the copper wires in your walls. It's driven by free, delocalized electrons just zipping along. It's a purely physical change, no actual matter is moving. But look at the right side, electrolytic conduction. This happens in liquids, specifically electrolytes like salt dissolved in water. Here, the charge isn't carried by tiny free electrons. No, it's carried by the physical movement of actual chunky ions, charged atoms. Because physical matter is literally moving to carry the current, this is a chemical change. They are fundamentally different processes.
And that perfectly tees up section 3, forcing chemical change. Once you realize that ions can actually move to carry a current, you can start using electricity to do some serious chemical heavy lifting.
If you take nothing else away from this explainer, let it be this. This is the core aha moment. There are 2 main types of electrochemical cells, and they are perfect, beautiful opposites. Electrolytic cells take electrical energy, like plugging something into a wall, and convert it into chemical energy to force a stubborn, non-spontaneous reaction to actually happen. Galvanic cells, they do the exact reverse. They take spontaneous chemical energy and convert it into electrical energy. One uses raw power to create chemistry, the other uses chemistry to create power.
So let's zoom in on those electrolytic cells for a second, where we're forcing reactions. You've got to track the electrons. And to do that, chemists use 2 classic mnemonics, red cat and anox. Red cat tells you that reduction, which remember is the gaining of electrons, always happens at the cathode. Anox tells you that oxidation, the losing of electrons, always happens at the anode. Whether you're charging your phone or electroplating a piece of jewelry, red cat and anox are the absolute undisputed rules of the road.
Watch how this actually plays out in a real circuit. It's like a perfectly choreographed dance. Step 1. The positive ions, the cations, migrate straight over to the negative cathode. Right on cue with red cat, they gain electrons and are reduced. Step 2. The negative ions, the anions, migrate to the positive anode. True to anox, they lose electrons and are oxidized. And step 3 is where it all comes together. This oxidation and reduction happens simultaneously. The exact number of electrons being lost at the anode is instantly being gained over at the cathode. It is just a flawless synchronization of chemistry.
You might be wondering, why go through all this trouble to force these changes? Well, the industrial applications are absolutely massive. By using electrolysis, we can extract pure elements out of salts. We're talking producing pure sodium and chlorine gas literally just from table salt. We use it to purify copper so our electrical grids don't fail. We even use it for electroplating, dropping a super thin, gorgeous layer of silver onto something like a cheap iron metal to protect it from rust. Honestly, electrolysis is basically the invisible engine driving modern manufacturing.
All right, let's flip the script for our final act. Welcome to Section 4, Harnessing Chemical Power. We just saw how electricity forces chemistry. Now, let's look at how chemistry spontaneously gives us electricity.
So, galvanic cells, sometimes called voltaic cells, these are electrochemical cells where spontaneous redox reactions generate electricity. Simply put, this is just the textbook definition of a battery. You don't plug them in, the chemicals inside already inherently want to react with each other. By physically separating those chemicals and forcing their electrons to travel through an outside wire to get to one another, we intercept that energy and use it to power our stuff.
There are a couple of major categories you'll run into. First up, primary galvanic cells. The defining feature here is that they are totally non-rechargeable. Once the chemical reactants inside are used up, that's it, the battery is dead. You've got your old-school Daniels wet cells, which literally use sloshing liquid solutions, but more commonly you have standard dry cells, your zinc-carbon Leclanche cells, or the alkaline batteries you constantly have to replace in your TV remote or flashlight. Use once and toss.
Now, those early primary cells, like the Daniel wet cell, relied on a genuinely genius component called a salt bridge. See, as electrons flow out of one side and dump into the other, the electrical charges in those separate liquid compartments get totally out of whack. Without some kind of intervention, the battery would stall out basically instantly. The salt bridge is the unsung hero here. It's a paste connecting the two sides that seamlessly feeds ions to maintain perfect electrical neutrality. It allows the current to keep flowing while physically preventing the reactive solutions from mixing and ruining the whole setup.
But hey, throwing away dead batteries is a pain, right? Enter secondary galvanic cells. These are the rechargeable ones. Take a standard lead-acid car battery. When it's fully charged, you have pristine reactants, lead and lead oxide. You turn the key, it discharges, giving you spontaneous power, and both of those turn into lead sulfate. But here is the brilliant part. As you drive down the highway, your car's alternator pumps direct current power back into the battery. It literally temporarily turns that galvanic cell into an electrolytic cell. It forces those lead sulfate products all the way back into the original starting materials. You are literally reversing the chemistry just by reversing the current.
Which leads us to the ultimate frontier, fuel cells. A fuel cell continuously turns chemical energy into electricity just like a battery. But instead of trapping all the chemicals inside a little metal can, you constantly pump the fuel in from the outside. These things are so incredible they actually power space vehicles using nothing but gaseous hydrogen and oxygen. They pump out indefinite electrical energy for the astronauts, and the only byproduct they leave behind? Pure, drinkable liquid water. It is clean, it's efficient, and it is wildly powerful. So the question I'll leave you with today is this. If mastering electrochemistry can cleanly power human life in the literal vacuum of space, what other frontiers right here on Earth is this chemistry going to unlock for our future? Thanks so much for joining me on this explainer. Keep asking questions, and I'll catch you in the next one.